over. Okay, so we missed that stuff, but this stuff is pretty simple. The read cross is used to upload your information. The parameters can be accessed on the help page. For our purposes, again, we use the CSV format, four-way cross type, and alleles are set, or genotypes are set to null. Okay, so on to the second function that can be used. Jitter map. Jitter map isn't always necessary for people's use whose pipeline looks different from ours, but since our map comes from LutMap, how LutMap handles markers that are probably really close together and nearly identical in their genotypes, it often, if they're close enough to identical, it will collapse those markers to the exact same centimorgan position. And so you might have two markers that are both at like 1.15 centimorgans. But our QTL can't handle markers that are set at the same position. Fortunately, they've made this jitter map function that can allow it to convert maps that have more than one marker at a certain position into non-identical marker positions.
So this function will handle the duplicate position.
Yes, what it does, like it's literally what the name sounds like. It like shuffles the map just like ever so slightly. For example, the default for jitter map for shifting positions, it's what is that, like a millionth of a centimorgan, it shifts it. So it's still, in terms of like analyzing the results, it's still pretty much the same position, but the number is just different so that our QTL can separately identify which marker is being referenced.
So as long as we use this function.
Yeah.
So if we use this function, then it will do.
Yeah, it'll shift it ever so slightly. I think usually, trying to see if I have an example. I usually set, in this example down here at the bottom, I usually set it, the amount that it jitters it to this number. And that's because when you're analyzing, it's still pretty much the same position. But when you're getting the results, usually our QTL only displays the positions to that fit fourth position. So then you can differentiate when you're referencing to the map from some of the results. You can leave it as default if you want. That's just my preference. So it's easier to reference stuff in the map.
The default is busy or
if you don't set, in this example, if you don't set this amount equals, if you don't set a number there and don't include the amount equals, it will default up here to this 1 to the -6. And this is the jitter map help page. It's a lot shorter than the read cross because there's a lot less parameters that you can define. All you need is an object, which has been defined from the read cross function. And so you just put it, like in our preliminary example, we had read cross and we had also assigned this to qtl.data. So we put the qtl.data in the jitter map function because that's the object. And it says here in the parameters, it needs to be a read cross object. And then we can also define this amount, which I've set to differ from the default and to do it to this number.
So this function should be inserted before our QTL calculation.
Yes, this jitter map has to be used after the read cross, but before the subsequent function that we'll talk about, which is the calc geno probabilities. Because you might have noticed that in this example, these two, the object that's getting written to is the same as the object that's within this jitter map. That's because jitter map isn't just writing a new map, it's kind of overlaying this information into your existing map. And so you still need all of the other data that goes along with the file that you read into RQTL. And so these names are usually the same. You can set them differently, but it's just easier to keep track when you have one object that you're editing. Okay, so after using JitterMap, we can go to this calc geno probabilities. This step has to be done prior to scanning for any QTLs because it does some intermediate calculations. Namely, it calculates the probabilities of the genotypes being correct, which since our genotypes come out of LetMap and they're already somewhat of estimations, and I say estimations in the sense that they might be slightly different than what we genotype them as, but they're probably correcting for any genotyping errors or some stuff like that, since they do come out as phased data from LetMap. So for our cases, calc.geno probabilities probably isn't doing too much work, but it's just required to perform this before we move on to QTL mapping. And so in this example, this calc.genoprob, again, we have this same object that's getting defined, this QTL.data is what we're performing this function on. We're setting the step to 0, which I'll explain that in one slide. And then the error probability is getting assigned to this, and it's getting written back over that same object. And so what some of those parameters mean, essentially, if we read this description, we're using some models to calculate the probabilities of the true underlying genotypes versus if there's any genotype errors in the data. And it gives allowances in the data file if there are any potential genotyping errors. So in our usage, we see that we have our cross object, which we usually have as the QTL or cross.QTL. The step, if we come down to defining what that is, it's the maximum distance between positions at which the genotype probabilities are calculated. Essentially, keep in mind that RQTL was, I think, first published as a package in like 2003. So again, some of its more preliminary things are operating under the assumption that we're making a map possibly of a lower density than what we currently do with our various types of SNP markers. And so what this step function does is it calculates the genotype probabilities both on the markers, and it can calculate in intermediate regions between the markers. Like for example, if we had markers that had a gap of 10 centimorgans in between them, it can calculate the step is the distance at which you want to be sure that there is a genotype probability evaluated. So that instance, if we set the step to 5 and there was a 10 centimorgan gap, we would have one genotype probability evaluation in between those markers, even though there's not a marker at that position. Since our maps are pretty high density, and doing this step function can give us QTLs at positions that don't exist as markers, I usually set step to 0, and that means it's not performing any calculations in between the markers. It's only doing the genotype probabilities at each marker. The error probability is just our error rate that we use. Usually the default is this, and I think that's what I had in my example. Like other QTL mapping software, you can set the type of mapping function that'll be used to any of these 3, Haldane, Kosambi, CF, Morgan. I believe I don't remember if I define that, but that's an option if you want to use one of those specifically. Those are all of the different, oops. Those are all of the different parameters for this CalcGenos. And so finally, or not finally, next is this scan1 function. And that's kind of the most important function that actually does the evaluation of potential QTL models. And there's several different ways to model QTLs. You can have models that evaluate just a single QTL, or you can have models that evaluate the presence of multiple QTLs. What scan1 does is it scans just for a single QTL model, which is the most simplified QTL model. And it's good for using, it's good for scanning for major QTLs. They'll show up pretty apparently in this scan1 function, but sometimes for traits that you might have multiple like minor QTLs that don't have a very good LOD score, you may need to proceed after this scan1 using a multiple QTL model. Basically, the output from this function is an LOD score for the marker and trait association. And that score is evaluated for every marker on the map. And so in our example, we define the function scan1. The object that we're writing it to now is different than our QTL.data, but QTL.data is still our read cross object with some stuff written on top of it. And so we put that in as the input data for this function. Additionally, we need to define which phenotype that we want to evaluate for QTLs. And we can just define which column that phenotype is located in. And we use a number because in our initial RQTL CSV file, we had all of the different QTLs in different columns at the beginning of that file. And you can just reference that file. And if you want to evaluate column 2 or 3 or 4 or 1, if you only have one phenotype, you do those separately.
Does that output come as a long list or a table? Or
yeah, it's a long list. The QTL scan1, I can show you in a minute what that looks like, but it's basically just a long data frame is what it's called in RQTL, but like it looks similar to what an Excel file would look like. And it has all of the marker names as row names. And then there's a column that just has LODs for all of them. And I think there's also, it also lists the centimorgan position and the chromosome in that file in case you're looking for a specific marker. But scan1 can also be used for calculating the permutation test. And permutation tests are important because they're what allows us to evaluate a significance level that's applicable specifically to this data set. And so if you're not familiar with permutation tests, essentially it randomizes the genotypes and the phenotype data so that it randomizes it so that there should be no linkage between phenotypes and genotypes, since it's now completely random. And then at that stage, it evaluates what the highest LOD score could be from that data that should have no linkage. And at usually like the top 5th percentile, so like an alpha value of 0.05 or the 95th for your significance, usually that is the number that is used for the permutation threshold. And generally, permutation tests are repeated like 1,000 times so that you have good replication and you approach whatever the 95th percentile would be under like infinite times.
But it's not computation. The function is one of the most important functions try to determine the threshold.
Yeah.
Right. So the more you run. Supposing you can get more.
Yeah, because like, since this is a randomized test, like if you only did like 10 times, that like 95th percentage could change between like 4.1 to 4.2 to 4.3. But as you increase the number of times and capture like more instances of randomizing this data, you kind of approach a stable number that is your, I wouldn't say true, but like the more, just more stable number for your permutation threshold. And the way that we calculate the permutation test using our QTL is with that same scan1 function. And we set the first two parameters exactly the same as our phenotype data, because you have to since it randomizes the phenotypes and the genotypes, you have to do a separate permutation test for each of your phenotypes. You can't just do one and use it for all of them, because then it's not calculated specifically for that phenotype. But those two are left the same. And then just here at the end, you do n perm, which basically stands for number of permutations. And for a final permutation run, you can set it to 1,000. If you're doing some preliminary calculations, you can set it to like 100, because that'll be pretty close. But the final time where you want to know the actual permutation threshold, it's pretty standard to do it 1,000 times. Any questions about permutation tests? If not, this is the scan1 parameters. Just going to keep zooming in.
So it does all that when you put in scan one?
When you do in scan1, these are all of the possible parameters that you can set. Some of them have defaults, some of them do not have defaults. For example, the cross object, that is our qtl.data object, we can set that, and that has to be set or scan1 won't run. So there's no default for the cross object. The chromosome can also be defined if we want to only look at one specific chromosome instead of all of 19. The default is all chromosomes, but you can set it to just one chromosome. Additionally, the pheno.call defines the phenotype column. The default for that one is column 1. So if you don't define this, it will only analyze column 1. The model, you can set any of these. I never mess with any of that stuff because we have a normal model, but you can also set it for binary data or non-parametric stuff. Again, there are different methods that can be used here. Down here, it defines all of them. The EM algorithm, imputation, Hartley-Notts regression, all of that stuff is just kind of like the statistics of how they arrive at the scan1 results. You can also add covariates, which for a lot of data isn't necessary, but like, I know you guys have heard me talk about the cold hardiness data before, and since that's so influenced by weather, in that instance, we used a temperature index as a covariate to try to capture that environmental data into our QTL model. You can also have interactive covariates, and that is, again, like a more complex. It has to do with like kind of how there's interactive QTLs. I have not used that previously. The default is null, so generally you don't have to worry about it. You can weight the individuals. I'm not sure under what instances you would do that, where our data doesn't really need to be concerned with it. There's some stuff to define which observations to use. I'm not sure what this upper even is because we don't use it. I think the next thing that we use, you can also define the start point on the chromosome. So if you only want to do like the second half of the chromosome, you could define chromosome 2, and we only want after 60 centimorgans, so you could define the start as like 60, and that would do that. For most like instances of actually looking at the data, that's not really that useful. It'd just be if you wanted to get a zoomed in view for some reason of just that data. The number of perms, that is what we defined in our permutation threshold. You can also set some things for X chromosome specific data. We don't use that. And we don't usually use any of this other stuff. And again, all of those functions are defined in this whole page if you're ever concerned about what they stand for. Okay, the plot function, that's the function that actually allows us to visualize the results of the scan one. Essentially what it's doing is creating a line graph which separates all of the chromosomes and then lines up the markers on the x-axis according to their centimorgan position, and then the y-axis is the LOD score of the marker trait association. And there's a couple of different ways we can do this. If we want to look at all 19 chromosomes with none of the extra stuff, you can just do plot and then the scan1 object, which was qtl.scan1. Additionally, you can set some other parameters if you want to get, for example, a more zoomed in view of one specific chromosome, and you want to also see the marker names. So for this example, we have our scan1 object. Maybe we want to look at just at chromosome 2, so only chromosome 2 will be displayed in the plot. We can also include tick marks for all of the different markers, which I've set to true. I've also set show markers.names to true, and that will allow us to actually have the marker names on the x-axis. And then I've set a limit, an x-axis limit of 60 to 90 if we just want the markers that are located between 60 centimorgans on chromosome 2 and 90 centimorgans on chromosome 2. This would be an instance if we wanted like a zoomed in view of a specific QTL. The plot function is a little different because plot can be used for all sorts of different data outside of the RQTL package. But what RQTL does, it actually has its own specific plot.scan1 function. But when you use the plot function on a scan1 object, it passes you through kind of to the like true function that you're using. But it simplifies it and allows us just to type this in the code window. But if you need to access the help page, typing in plot won't give you information specifically for doing plots on scan1 objects. Instead, you need to use this plot.scan1 parentheses. And like I said before, there's a number of different parameters that you can set. You can plot up to 3 different scan1 objects. For instance, if you had 3 years of data on a single trait, you could layer those on top of each other with the different lines in a single plot. Again, you can define the chromosome. You can define the LOD column if there's more than one. You can include the markers, which I talked about. You can set X limits for the centimorgan limits. You can also set Y limits for the LOD score limits. LTY stands for line type. You can use different numbers to use different line types. More information is available on that online because R has a set of like 1 through I think 30 different line types that are just defined by the numbers. And those are standard from RQTL packages through all the other packages. You can use different colors for the different lines, and you can define colors. They have preset colors for some more basic color names. So you can set black, blue, red. LWD is line width. The default is 2. That usually works fine, unless for some reason you'd want thinner or wider lines, you can edit that. Add and gap, I've never used those before. You can change the tick marks types. I don't know why you'd want a triangular tick mark, but you can do it if you want. The show marker names, the default is false. We can set that to true if we do want to show the marker names. You can set alternate chromosome IDs. That would be an instance if you hadn't renumbered the linkage groups correctly coming out of your mapping and you needed to renumber it to the actual chromosome numbers. Band color, I'm not sure what that does. Oh, the band column or band color, if you want to show distinctions between like chromosome 1 and chromosome 2, when you split all of them, you can do some banding to have the chromosomes be different colors in their background. CEX can enlarge or decrease the size of the text on the plot. And some of this other stuff is also to do with more minute changes of the plot. But the basic stuff is kind of what I've shown in the example. Okay, so in summary, these are examples, and I'll run this through our QTL to show you guys, where did that go? What that actually looks like as far as our data is concerned.
This is, so you use only the scan one or the single, when you did the cold hardy, did you use the multiple models for berry?
I did the berry quality stuff on map QTL, so I wasn't using RQTL. I did a type of multiple QTL model. It's not the MQM mapping that RQTL uses. You have to actually like create a model that's like this chromosome or this QTL on chromosome 1 plus this QTL on chromosome 2, kind of like defining cofactors, but a little different, and then analyzing that. And there's some different functions to use that. Unfortunately, RQTL does have an MQM mapping function, but it doesn't work with 4-way cross types, so we can't really use it. There's more details on doing multiple cross type or multiple QTL models in the RQTL, what's it called? Like the PDFs for the instructions. They have several guides that are put up online that do a better job explaining them than I could.
So the current in R script, you have only single, not a multiple.
The stuff that's commented out below in that R script is a way to do the multiple QTL modeling.
We brought the single in R script.
Yeah, generally speaking, if you don't know how to correctly use the multiple QTL model one, it's better just to do the scan one.
Multiple times.
Well, no, like
No, it's different.
if you truly have data that'll give you good results with a multiple QTL model, you can get higher LOD scores with the multiple QTL model than you can with the single QTL model. Similar to how when you select cofactors on the map QTL, you get a little bit higher LOD scores doing that on that other software.
See, that's my question. So is that true that the RQTL versus we call it QTL 6,
Mhm.
right? I mean, which one? It's better because I know QTL 6 you could add a lot of cofactors
Mhm.
to make the QTL number better. But other publications, especially from the Vitagene, you can see the QTL, the OD number is quite low,
Mhm.
but they still being accepted.
Mhm.
So what's really the difference in between?
Well, like the MQM mapping function that we generally use, or the RMQM in the map QTL6 program, like the mapping methods are, the statistics behind it are different versus doing a multiple QTL model in our QTL. if you can create the model properly in RQTL, I think you should be able to obtain like similar results. I don't know if the LOD scores would be exactly the same. It's just harder to do it in RQTL. And additionally, when you do, there's a function called like stepwise QTL or something, and it calculates the probability of some of those multiple QTL models being correct. You also see the data of whether this multiple QTL model that you can technically get some significant QTLs on is less probable than no QTLs being in the model. And I think that's something that's not really sometimes considered with the multiple QTL model.
See, the reason why I asked this question is our Downing Melville paper published in 2019. Why is QTL 6? For sure, that LOD shoots up to 18.
Yeah, and in instances where it's a really high LOD score, that's not an issue. You can do scan 1 and call it a day.
See, but our case at that time was already also did RQTL. But we just added data not showing it's agree with the data. Because at that time, I don't know, he never showed the RQTL data. Whether the LOD is way low compared to 18 or not, that I have no idea.
No, it's the plot a little bit lower, but the thing is because they are not sure master, not sure.
Additionally,
but right now, for the QTL plot, right now, actually for publication is really not necessary.
No.
One table is more than enough than that.
Yeah, especially if you're doing something past scan 1, you don't need to show all of the different.
Right, and also if you have multiple trades right now, actually for berry acid and tandem, we do have it. So one table is good enough. You don't need to show individual QTL plot.
No, I think papers are moving away from that.
So the research trend is really totally going to different directions. We'll say like you're well, I'm going to send you that Vitagene 2 slide back to you because I changed somewhat. Okay, for take up yours is you didn't say what kind of trade it is. You only say ability, routine ability. But what you measure is that do length, accelerate roots, or whatever. You need to define that. Okay. See,
You mean list the phenotypes?
yeah, but routine ability, how to define the routine ability? You have 1 on chromosome 2, right? That one you need to define. You can just say, just say the root length, okay? But that is simple, but I want you to fix that slide. But again, go back to that. For yours, I mean, berry quality, right? Or acids with tannin, for yours, the routine ability. Right now, no longer we need to get the QTL plot anymore, but it's just more than one trade in one paper now. You know, I'm talking about like how you define your routine ability. So you need to start to think about, I mean, is that every single one, you're going to have a QTL. And when you, every single trade, you're going to have a QTL, then which model you're going to use? You know, and so Carly, so how tedious when you use QTL 6 versus our QTL?
I would say like defining the multiple QTL model in RQTL is more tedious because you just have to run more functions. I don't remember what the calculation times were on what's it called? MapQTL 6, but RQTL is probably faster at doing them.
Right. I can imagine RQTL probably will be faster, but which one is more? I don't know how. Yeah, I don't know how to.
For multiple.
It's easy to check stuff for sure in RQTL because you can just run this and you can see single QTL scans of all of that stuff. As far as like selecting cofactors and whatnot, I would say it's probably more user friendly on MapQTL 6 just because you have a graphic user interface.
again, we're going to use that, QTL6 as the major, software for mapping the QTL, but then still using the RQTL to confirm that position is
No,
correct
I
or
think,
not.
no, that's not one way we can do it. After we run the R, there's the output file. So as long as you have output file, you can separate if there are 19 chromosomes, whichever you are interested in, you can output one of them, go into the QTL6. That would be the most easier way.
You probably could, yeah.
But my point here is, again, we don't need to show the QTL plot
No.
anymore, right? So whatever on the table with multiple trays with a LOD value, that's the most important thing, right? So then which program or which software we're going to do? I think, well, we will see the.
Yeah, I think what will kind of determine that decision, number one, how like invested somebody can get in RQTL, because if you can figure out how to do it, I would recommend doing it in RQTL. I'm just saying it's probably going to be harder from somebody starting from like nothing
Sure.
to do it in RQTL. And how like significant your results are. If you have like really significant results, do it in RQTL. You can just do a scan one and call it a day. But if you need to do like the cofactor selection and whatnot in order to get like several significant like minor QTLs, if somebody's not familiar with how to use the software, it's probably going to be more difficult to do it in RQTL.
See, I bet for your cohortiness, if we use, for say, SSR with RAM6.
I would do it on RQTL.
RQTL.
Yeah.
Right, okay. But then the number might be really low.
Which, if it's low numbers, it's going to be also low on RQTL.
Okay.
I don't think that the LOD scores aren't like that different.
RQTL is low, that also will be low on the QTL.
Yes, most likely.
Okay. So then we will see the biggest, I think the student from this lab, if they have the capacity to do both, that would be wonderful.
Mhm.
Because not that many people really knows how to do this,
Okay, I'll show you guys an example of what some of that stuff looks like. I'll use this, here, I'll zoom in. Okay, so at the top here, I just set my working directory. This is the folder where all my files are. The library that I say RQTL all the time, that's just meaning like it's the QTL package in R. So the actual library name is just QTL. We run that to make sure that the package is opened and we can use all the functions in it. And then coming down here, we have our examples that I showed you in the data or in the slides. Our read cross object, we have CSV, the correct name, genotypes, null, cross types, 4-way. So we run that. And I'll point your attention down here to the bottom where it says some markers are at the same position on all of the chromosomes. And it tells you to use the jitter map function over here. And so we know that's the next thing we need to do. But just quickly, I'll show you what the object coming out of that read cross function is. So like I said, it takes that like single pane or single like sheet of data that we read into it, and it separates it into the genotype data, the phenotype data, and the map data. So we have QTL data, that's our object. It says the details about it. And it also has a geno section and a pheno section. So the geno section has 1 through 19 sections within that because we have our 19 chromosomes, and that has our genotype data and our map data within all of those different chromosomes. The phenotype data has the titles which were defined in the column headings in that file that we read in. So this is cold hardiness data. We have our monthly temperature or monthly LTE data, and then the temperature indexes, since in this data I used those as cofactors. And we have all the different columns of phenotype data that were present in that file. So next we need to run the jitter map. The jitter map doesn't show anything. It's not going to really look that different in the actual object, except now, like previously, these 4 numbers were all listed as zeros. Now there's 2 replicates for each of these marker positions, because I think our QTL can handle technically separate male and female maps. So when we're looking at it like this, there'll be 2 instances of each number, but that's a single marker. So we have 1 marker, 2 instances of 0, and then the next one that was previously also a 0 is now this 0.001. And that's like what I was saying with why I set the amount on the jitter map to this value, is because that's all the digits that get displayed in our QTL. So it's just easier to visualize. Okay, so next is the calcs probability. We have the stuff set the same as in our example. This runs, and we're not going to see anything in our data. Our data is going to look the same. It just adds some stuff like in the bottom layers, kind of, so to speak, of this object. And then finally, our QTL.scan1 function. Oops. I accidentally clicked our permutation threshold, or that's going to take too long. Okay, so I'll run the QTL scan1, and that's doing, we'll change it to phenotype column 1 because the second column is actually a cofactor. And it says, it gives me a warning message here, and that's saying it's dropping 26 individuals with missing phenotypes. That's just because in this data set, we've included all of the individuals which we have phenotypes for across 2 different years. And so not all individuals will be present in both years. And so for column 1, there's 26 individuals that have like missing phenotypes, but that's fine. 26 is a low enough number. I haven't noticed that it really starts affecting stuff. Usually when you get up to closer to like 40 or 50 individuals that are getting dropped from the phenotype, it has more of an effect, since usually we only have at most around like 200 or 150 different phenotypes at a time for our populations. And so the object that comes out of that was our QTL scan1 object. And we can see that listed here next to the QTL.data object in our environment. If we click on that, we'll see that table that I was talking about previously. We have our marker names in the row names down here on the left. Next is the chromosome and the position in centimorgans on the map. So these first 3 columns are just our map data. And then this final column is the LOD score between the chromosome and the marker and the phenotype that we defined in our scan1 object. And so we can see we have LODs of like 1, pretty close to 2 for much of this data on chromosome 1. And right now, the data is sorted just according to mapping positions. So chromosome 1, then 2, then 3, and so on. And our positions are also in order from 0 to 100, or however long that chromosome is. If we use this 3rd column or 4th column to sort the data, we can get the lowest LOD score that's present, which is on chromosome 10. Or if we sort it one more time, we can do the highest LOD score, which appears to be on chromosome 11. Which is almost LOD score of 4. So that was the scan1 data. If we run the permutation test, I'm going to set that pretty low just so it goes quickly. But we have to make sure that the phenotype column is set to 1, since our scan1 data that we used was also for phenotype column 1. They have to match. We'll run that, and it runs the permutations down here. It does 1 through 10. Again, 26 individuals were dropped for the same reason as previously. And that has been set to this permutation test object that we can see over here. Now, if I click on that, if we did more, this list would be longer. But this is the highest LOD score that occurred in all of those permutations. And so we can see, if we sort this, it goes from about 2.25 all the way up to 4.6 almost. And the way that we get our actual LOD threshold is doing, you can type summary permutation test and that object, and it'll give us the 5% and the 10% down here on the bottom. And the 5% LOD threshold is about 4.17. So if we look back at our scan one object, we see that our LOD score, even though it's pretty close to 4, it's below our permutation test threshold. And so it's likely not significant. And then if we want to visualize that stuff, we can use the plot function. And I'll show you what both the full version looks like. This is the full QTL plot that has chromosomes 1 through 19 here at the bottom. These kind of black bars are technically tick marks, but because it's so condensed, you can't really differentiate between all of them. And so there's a little bit of a gap between each of the chromosomes, and this kind of line graph is the LOD score for each of these markers given the trait on phenotype colon 1. If we want to see, for example, what chromosome 11 looks like, we can look at that more specifically. And so that looks really like stretched out. But this is that chromosome 11. So we see it's kind of high up here. And then as we move farther away from what we would expect, if this was significant, farther away from what we would expect the QTL position to be, it decreases. And now along the bottom, we can actually see those tick marks. And so each of these tick marks represents a different chromosome, or not a different, sorry, a different marker. Yes, a different marker along this now single chromosome. And we can see the actual centimorgans here defined across the bottom. So it looks like chromosome 11 is only about 65 centimorgans in length.
So that high is the one close to 4. Sorry, that click down there, you're going to see the marker's name?
If we want to see the marker name, we can't click on anything. We have to define that in the function. So that was, and like, for example, I don't exactly remember what that parameter is. So I'm going to do question mark plot dot scan 1. And it'll tell me exactly what to type in. And that was show dot markers dot names. The default is false. If we change that to true, I believe that should, this looks funny because it's so small, but if I zoom out, this would be an instance, okay, we're only really concerned with about 0 to 30. And so in order to more easily read those chromosomes, we could define the x-axis limit. X-lim equals, I think, 0 to 30. I think that I seems to have typed. No. Now we only see 0 to 30, and we can a little more easily see these names. But that's kind of like what I was saying. It's hard to do some stuff sometimes on these more dense maps.